Chapter 4, Throughput. We pop a 4 and we append C4. The new constraint, read throughput and independently write throughput, can each exceed the computational capacity of a single machine. Vertically scaling CPU and memory to absorb this load is expensive and, past a point, impractical. Notice the word independently. Those are two separate ceilings, and they lead to two different architectural responses. Hitting the read ceiling is answered by adding machines that serve reads. Hitting the write ceiling is answered by adding machines that accept writes. Those are not the same problem, and the architectures that follow are best understood as answers to one or the other. Before we scale out, though, there are several general mitigation strategies available, either before scaling out or alongside it. Queuing is temporarily buffering incoming requests to be processed once capacity becomes available. You pay in latency. Load shedding, deliberately dropping or rejecting a fraction of incoming requests to keep the system within capacity. You pay in availability. Back pressure, a flow control mechanism in which a downstream component signals an upstream component to slow or stop sending further requests. You pay in end-to-end latency. All three of these trade throughput stability for increased latency, reduced availability, or both, and none of them increases the system's underlying capacity. That's the crucial sentence. They buy you time, they do not buy you headroom. A fourth mechanism, rate limiting, is often applied at admission rather than under saturation. Each client tenant or key is granted a fixed quota of requests per unit time, and requests beyond that quota are rejected or delayed. Common implementations include the token bucket, the leaky bucket, the fixed window, the sliding window counter, and the sliding window log. Now, before we look at the mechanisms that genuinely add capacity, this is the natural point at which to introduce one of the foundational results in distributed systems theory, because everything that follows in this chapter is a response to it. The CAP theorem, in the presence of a network partition PCA, a scenario that cannot be avoided in any real network. A distributed system can guarantee either consistency, making it a CP system, or availability, making it an AP system, but not both simultaneously. The PACELC theorem extends CAP by additionally addressing the common case in which no partition is occurring. In the presence of a partition, a system must choose between availability and consistency. Else, that is, during normal operation, it must choose between latency and consistency. So, laid out as a table, CAP is governed by the condition of a network partition, and its trade-off is consistency versus availability. PACLC, under partition, gives you availability versus consistency, and PACLC in normal operation, the else branch, gives you latency versus consistency. That else row is the one that governs almost all of a system's operating life, which is precisely why PACLC is the more operationally useful statement of the two. These two results make explicit some of the most fundamental trade-offs a distributed systems design must resolve. Their terms are defined precisely as follows. Consistency, in this network partition sense, means that every read receives either the most recent write or an explicit error. We'll refine this shortly into a spectrum of stronger and weaker models. And note again, this is a distinct notion from ACID's consistency despite sharing a name. That's the second time this collision has come up, and it will not be the last. ACID C is an application invariant. CAP-C is replica agreement. The letter is shared, the concept is not. Availability means that every request receives a non-error response without any guarantee that the response reflects the most recent write. A system may also operate in a state of partial availability, in which only some requests can be served. Partition tolerance means the system continues to operate despite arbitrary message loss or the failure of part of the network. One more thing about CAP that's frequently misunderstood. C and A here are binary, worst-case notions. A system either satisfies linearizability or it does not. It is either available or it is not. That picture is deliberately coarse. Sections later in this chapter give the graded version, namely, which point on the consistency spectrum a specific replication configuration actually achieves and at what latency cost. A system is not CP or AP as an identity. A specific configuration lands on a specific point of a spectrum. And a note on scope, because this is a place where the framework earns its keep. This chapter still operates under the assumption of a failure-free, partition-free network. S7 has not yet been relaxed, so the partition that CAP describes has been named, where it cannot yet actually occur. We introduce these theorems here anyway, because the replication mechanisms we're about to discuss are largely a response to the availability versus consistency and latency versus consistency trade-offs that these theorems describe. Network partitions themselves and their operational consequences are treated full in Chapter 7. So, let's turn to mechanisms for absorbing throughput beyond the capacity of a single machine, beginning with the case where only read throughput exceeds that capacity. The primary tool is replication, the practice of maintaining multiple copies, called replicas, of the same data on different machines in order to increase availability, increase read throughput, or reduce latency by serving reads from a replica nearer to the requester. Replicas must be kept synchronized with one another, and three major replication architectures address that problem in three different ways. Single leader replication. One node is designated the leader, all others are followers. The leader accepts and locally executes all write requests, then propagates the resulting updates to every follower in the order in which they were executed. Reads may be served by the leader or, to increase read throughput, by any follower. That single ordering point is the source of all the strength this architecture has. There is one log and one order. Every replica applies the same sequence, so each one exposes a prefix of that same sequence. This architecture scales read throughput easily by adding followers. But write throughput remains bounded by the capacity of the single leader, which becomes a bottleneck once write load alone exceeds what one machine can handle. So single leader replication answers only half of C4. The next two architectures address the other half, and they pay for it in ordering. Multi-leader replication. Multiple nodes are simultaneously designated as leaders, each capable of accepting writes, and leaders asynchronously propagate their local changes to one another. This allows writes to be accepted concurrently at different nodes, increasing both write throughput and availability since a client can always find some leader to write to. The cost is added complexity from write conflicts, which arise whenever concurrent writes modify the same data item at two different leaders. Watch how a conflict is manufactured on the diagram. Two clients, two leaders, one key, two different values, both accepted successfully. Neither leader did anything wrong. The conflict does not exist until the two writes meet. That's worth stating as a property. Conflicts are, by construction, detected asynchronously only once the concurrent writes are compared against one another. So how do we handle them? First, prevention before resolution. To minimize the frequency of conflicts, systems commonly route all writes for a given record, or all writes originating from a given user, through one designated leader. Conflicts then become rare by construction. Some systems relax even this constraint to further improve availability, accepting the resulting risk of temporary inconsistency. Where conflicts do occur, the resolution strategies include last write wins based on timestamps, UUID, or hash-based tie breaking, which is arbitrary but deterministic, combining a timestamp with a replica identifier, deciding by time and then by identity, ranking replicas by priority, a fixed notion of node importance, merging the conflicting writes so that both effects survive, or retaining all conflicting versions for later, application-level reconciliation. And resolution may be performed automatically at write time, at read time, or during background reconciliation, or manually, for example by prompting an end user to resolve the discrepancy. That last one is the familiar "which version would you like to keep" dialog. I want to flag one dependency here and flag it loudly because we will return to it twice. Last write wins is only as trustworthy as the clocks that produced those timestamps. A 6 is still in force. We still have one perfect global clock, so it works here. Chapter 6 revokes that permission entirely. Now there's a fundamentally different way to deal with concurrent updates, one that removes the need for a resolution decision altogether. Conflict-free replicative data types, or CRDTs, are data structures specifically designed so that concurrent updates never need explicit conflict resolution. Replicas are permitted to diverge temporarily as operations propagate asynchronously. When replicas synchronize, their states are merged using a merge function that is commutative, associative, and idempotent by construction. Take those three properties seriously because they're doing all the work. Commutative means the arrival order of updates cannot matter. Associative means the grouping cannot matter. Idempotent means duplicate delivery is harmless. Because the merge function's mathematical properties guarantee the same result regardless of the order or duplication of the inputs, all replicas converge to an identical state without requiring negotiation, and eventual consistency is guaranteed structurally rather than through ad hoc reconciliation logic. Contrast the two approaches directly. With conflict resolution, You detect a conflict and then pick a winner by some rule, which means a write can be discarded. With a CRDT, there is nothing to detect, divergence is self-correcting. Two clarifications. First, CRDTs achieve this through an algebraic merge and not through operational transformation, which is a distinct technique used in some collaborative editing systems. Second, be precise about what a CRDT buys you, eventual conversions, not linearizability. It buys you the absence of a conflict resolution decision. It does not buy you an ordering guarantee. One more structural question about multi-leader systems. How are the leaders wired together? The pattern of communication links used to propagate rights between leaders defines the system's replication topology. All to all, every leader communicates directly with every other leader. This maximizes redundancy of propagation paths at the cost of more complex ordering guarantees since messages can arrive via links of differing speed. Ring. Leaders are arranged in a logical circle, and updates are passed sequentially around the ring. This simplifies propagation logic, and each node needs only one outgoing link, but it can introduce additional latency, since an update may need to traverse several intermediate nodes. Star or tree. A central node forwards updates to all other nodes, or a tree of nodes forwards updates to their children. This is efficient to disseminate from and uses few links, but the central node is a single point of failure for propagation. More elaborate topologies are possible and are used in some large-scale systems, but the three trade-offs above are the ones that generalize. Now the third architecture, leaderless replication. No node is designated as primary. Clients or an intermediate coordinator send write requests directly to multiple replicas, and no strict global ordering of writes is enforced. There's correspondingly no leader failover mechanism, since there is no leader to failover from. Consistency is instead pursued through quorums. A write is considered successful once it has been acknowledged by W replicas, and a read is considered successful once R replicas have responded with the most up-to-date value among those R responses being returned to the client. A coordinator issues the request to all N replicas and waits for the requisite quorum to respond, returning an error if the quorum cannot be reached. The key condition is W plus R greater than N. That guarantees that every read quorum and every write quorum overlap in at least one replica, and that overlap is necessary for the read to observe the most recent write. Onlyation. I want you to notice the word I did not use there. I said necessary. I did not say sufficient. Hold that thought. We're going to return to it before this chapter ends, and the reason is genuinely surprising. W and R are tunable, subject to a trade-off between write latency and read latency. Set W low and R high, and you have a write-optimized configuration. Set them equally, and you're balanced. Set W high and R low, and reads are cheap. The constraint fixes the sum, you choose where to spend it. Anti-entropy mechanisms, introduced briefly here and discussed in depth in Chapter 5, run in the background to reconcile any divergence between replicas that quorum reads and writes alone do not resolve. Two practical matters before we move to the analysis. First, how do you add a replica? Adding a new replica typically involves taking a consistent snapshot of an existing node, usually the leader, in single or multi-leader configurations, and then applying every change made since that snapshot was taken in order using the write-ahead log. That's the write-ahead log's third appearance. It gave one machine atomicity in Chapter 1, and here it gives a cluster replica bootstrap. Second, how do partitioning and replication compose? In a partition database, each partition may maintain its own leader or its own independent replication scheme. That allows horizontal scaling and fault tolerance to be achieved along both the partitioning and replication axis simultaneously. Read the grid on screen as rows and columns. Rows are partitions, giving capacity and parallelism from Chapter 3. Columns are replicas, giving throughput here and later fault tolerance. Leadership is deliberately spread across nodes, so that every machine is a leader for something and write load isn't concentrated. Now, independently of which replication architecture is used, replication can be configured with different synchronization guarantees. These modes are orthogonal to architecture. Any of the three architectures can be run in any of these modes. Synchronous replication. A transaction is applied locally on the leader, then applied on every follower, and only then is an acknowledgement returned to the client. This guarantees that all nodes present a single consistent view of the data at essentially all times, at the cost of write latency bounded by the slowest follower. Asynchronous replication. The client receives an acknowledgement immediately after the local update on the leader completes. Followers apply the corresponding update independently and asynchronously at their own pace. Partially synchronous or semi-synchronous replication, a hybrid in which a subset followers is configured for synchronous replication, typically to guarantee some minimum durability, while the remaining followers replicate asynchronously. Watch where the acknowledgement sits on each timeline, because that single position is what determines everything else. In PACLC terms, synchronous replication is the else, prioritize consistency choice. Asynchronous replication is else, prioritize latency. And semi-synchronous replication tunes the mix by weighing how many follows sit on the consistency preserving path. It's a dial between the two extremes, not a third philosophy. We now have enough machinery to be precise about what consistent actually means, because so far we've been using the word loosely. And I want to start with a scope distinction, because these two families of guarantee are routinely conflated. Isolation levels from Chapter 1 govern the interaction between concurrent transactions on a single logical copy of the data. Data-centric consistency models, which we are about to define, govern how the multiple physical replicas of a distributed system are permitted to differ from one another, and for how long. Different objects, different guarantees. Ordered from strongest to weakest, strict serializability, which is serializability plus linearizability. It's the strongest available combined guarantee under which concurrent transactions appear to execute in a single serial order that additionally respects real wall clock time. Linearizability, a guarantee that the system behaves as though there were only a single copy of the data, but every operation on it taking effect atomically at some instant between its invocation and its response. Once a write commits, every subsequent read by any client observes that write's value on a later one. Sequential consistency, a guarantee that the result of any execution is equivalent to some sequential, interleaved ordering of all nodes' operations, in which each individual node's own operations appear in the order that node issued them, but without the real-time constraint that linearizability imposes. A single order exists, it just need not match wall clock order. Causal consistency, weaker than sequential consistency, requiring only that operations which are causally related be observed in the same relative order by every process. Operations that are concurrent, that is, causally unrelated, may be observed in different orders by different processes. On the illustration, a reply that was written after reading a post is causally after it. So no replica ever shows the reply before the post, but an unrelated write by a different user is concurrent with both and may land anywhere in either observer's view. And eventual consistency, the weakest of these models, if no further updates are made to a given data item, every replica will eventually converge to the same value for that item, with no bound on how long convergence takes, and no guarantee about what is observed in the meantime. These models form a strength hierarchy: strict serializability, then linearizability, then sequential consistency, then causal consistency, then eventual consistency. And notice that each step down removes exactly one requirement. First, the transaction grouping requirement, then the real-time constraint, then the single global order, then ordering for unrated operations, then every timing guarantee at all. Every step down that ladder buys latency and availability, which means the useful question is never is it consistent. The useful question is which of these five, and can the application live there? Now, independently of those replica-wide guarantees, a system may offer guarantees scope to a single client's own sequence of operations. These are often called session guarantees, and there are 4 of them. They're cheap compared to linearizability, and they cover most of what users actually perceive as the system being broken. Monotonic reads: once a client has read a given value for a data item, no subsequent read by that same client will return an older value for that item. Violate it, and time appears to run backwards for that user. Monotonic writes: a client's writes are applied in the order that client issued them. Violate it, and an earlier write overrides a later one. Read your writes: a client is guaranteed that any subsequent read it performs on a data item will return a value at least as recent as the last value that client itself wrote. Violate it, and you get the classic complaint: I just saved that, where did it go? Write follows reads. A write issued by a client after read is guaranteed to be applied to a version of the data item at least as recent as the version that the read observed. Violate it, and a reply attaches to a version of a post that predates what the author actually read. Under the network assumptions, still active at this stage. Remember, A5 is still in force. These guarantees are rarely violated in practice. Propagation between replicas is instantaneous, so only process delay from Chapter 1 can cause a follower to lag. Chapter 5 shows how real network latency makes these violations materially more likely, and these guarantees correspondingly more important to enforce explicitly. Which brings us to the analytical payoff of this chapter. We can now analyze which consistency models each replication architecture actually achieves, given the constraints introduced so far. And I won't put a standing caveat on the entire analysis before I give it. This still assumes a single perfectly synchronized global clock, since A6 remains active. Every row of this table is provisional. Chapter 6 revisits this exact analysis once clock synchronization is relaxed, so read this table twice. Once now, and once again then. Single leader replication. The leader can sequence every write locally, for instance by arrival timestamp, under the still active global clock assumption, and every replica applies updates in that same sequence. Under synchronous replication, that is sufficient to achieve linearizability. Under asynchronous replication, process delays mean a follower's applied state can lag the leaders. Write ordering is still preserved, so each replica always exposes some prefix of the same single write sequence, but a read served by a lagging follower may not reflect the most recent write. Linearizability therefore cannot be guaranteed for reads under asynchronous replication, though it still holds for the write sequence itself. Sequential consistency is not guaranteed in the general case either, and the reason is subtle. A client that writes to the leader and then reads from a lagging follower may fail to observe its own write, which violates the per-client program order that sequential consistency requires. It is recovered, however, once reads are routed to the leader, or once the session guarantees we just discussed are enforced explicitly. Absent those, the guarantee that survives is a consistent prefix of the leader's write order, together with eventual conversions. Multi-leader replication. Each leader executes its own local writes independently and propagates them asynchronously to the other leaders. Sequential consistency, which requires a single globally agreed order consistent with each node's own issue order, is therefore not achievable in general. Under the current assumption of a synchronized global clock, however, resolving conflicts by last write wins on commit timestamps correctly reflects true causal and real-time order. And because propagation is still instantaneous under A5, every replica applies writes in that same order, so causal consistency is achievable this way. Alternatively, eventual consistency alone can be achieved through weaker reconciliation strategies, such as ranking replicas by a fixed priority, that node importance notion from earlier. And because writes still lack a single enforced global order, even when timestamps are trustworthy, conflicts between concurrent writes remain possible and must be resolved by one of the mechanisms we described. This result is provisional in the strongest sense. It depends entirely on the trustworthiness of node clocks. Chapter 6 revisits it once that assumption is relaxed and shows that the more robust route to causal consistency is via version vectors rather than timestamp comparison. Leaderless replication. Here's where we return to that word necessary. Because the read and write quorums are guaranteed to overlap, W plus R greater than N, it might appear that linearizability follows directly. It does not. Concurrent writes may be applied in different orders at different replicas, so that fewer than W replicas end up reflecting each individual concurrent write. A subsequent quorum read using last write wins can therefore return inconsistent results, depending on exactly which R replicas happen to respond. And that's precisely what the counter example on screen shows. Two reads, one strictly after the other, landing on different quorums and returning different values, the later read returning the older value. Reads go backwards. There is no single copy illusion, so linearizability is out. Causal consistency, however, is achievable with appropriate anti-entropy mechanisms in place to reconcile the replicas that quorum operations alone leave divergent. The general lesson from this whole table is worth stating in one line. Ordering strength comes from having one place that decides order. Remove that place, and no amount of quorum arithmetic restores linearizability. Let me summarize Chapter 4. Under A4, throughput was never a constraint. A single machine could absorb any read or write load, so the question of how many copies of the data to keep and how tightly to synchronize them never arose. Constraint C4 removes that ceiling and, in doing so, forces the system to confront the CAP and PACLC theorems directly. Because read and write throughput must now be spread across multiple machines via replication, and because a network partition is an unavoidable possibility, the system must decide explicitly or by default whether it prioritizes consistency or availability when a partition occurs, and latency or consistency when it does not. The three replication architectures surveyed in this chapter are best understood as three different resolutions of that same underlying tension. Single leader replication preserves a simple, strongly ordered write path, and therefore the strongest achievable consistency, but it reintroduces a throughput bottleneck at the leader. Multi-leader replication removes that bottleneck and reduces write latency for geographically distributed clients, but it reintroduces conflicting concurrent writes, which the chapter's conflict resolution strategies and CRDTs address, either by picking a deterministic winner or by making the merge operation itself commutative and conflict-free. Leaderless replication sacrifices any single point of ordering in favor of tunable, quorum-based availability, whose W and R parameters directly trade write latency against read latency, and whose anti-entropy mechanisms are required to paper over the ordering guarantees that quorums alone cannot provide. The consistency models introduced along the way give this design space a common vocabulary, which is what lets the chapter's closing analysis show precisely which consistency ceiling each architecture and mode combination is capable of reaching. In practice, single leader synchronous replication is appropriate wherever strong consistency is worth its latency and availability cost, as in financial ledgers and systems of record. Single leader asynchronous replication, where read scaling matters more than absolute freshness. Multi-leader replication, where writes originate from multiple geographic regions, or must succeed even when connectivity to a central leader is degraded. And leaderless, quorum-based replication, where the priority is maximal write and read availability at large scale, and the application can tolerate, detect, or reconcile occasional conflicts. No architecture is dominant across consistency, availability, and latency simultaneously, which is precisely what CAP and PACLC assert. And now look at what we are still pretending. Zero network latency, one perfect clock, nothing ever fails. CAP's partition has been named, but it cannot yet occur. That is the honest state of our model right now. The next assumption to go is A5. Propagation stops being free, and every asynchronous arrow we've drawn in this chapter acquires a duration and a probability of failure.